Okay, guys. I finally figured out how to put audio on this. So here we go. Okay. Run the video. Okay, here we have a free body diagram. It looks like a car, as we have force and engine, force, normal force, frictional force, and gravitational force. I'm going to put my own symbols that I used in class for these, what they have on this diagram. So there they are. They should look familiar. Okay, the first question is this car in equilibrium? Why or why not? So equilibrium means all the forces are balanced. The vertical forces cancel each other out and the horizontal forces cancel each other out. Now, is that what's happening? What I just circled in purple shows that the horizontal forces are not balanced out. So net force horizontally is not zero. So there is a net force horizontally. The vertical forces, normal force and the weight, are balanced out. Okay, so is the car in equilibrium? No, because the horizontal forces are not balanced. What would be the net force? Fa minus friction. Okay. Let's go to the next question. Is the car accelerating? Well, if you have a net force, you have acceleration. That's Newton's second law. And therefore, yes. In what direction is it? Accelerating in the direction of the bigger force. So that would be to the right. Because F of A, the applied force, is greater than the frictional force. So yes, there is acceleration. Let's go to the next question. If you knew the magnitudes of each of the forces, how would you calculate the net force on the car? Well, if you had the force, applied force, you take the bigger force and you subtract the smaller force from it. So I'm going to try to catch up with my video here. So if the force of the engine was known, applied force, and the force of friction was known, I would just simply subtract the two. So it's always bigger force minus smaller force. Usually weight represents the weight of the car. Force of gravity, that's weight. Mass of car is kilograms. Mass is always in kilograms. So what's the weight? There's the equation W equals mg. Just plug in the values. Be sure you know that kilograms is the mass. G is the acceleration due to gravity. We don't put the negative on it when we're doing dynamics. So it'll be 1,500 times 10, 15,000 newtons. Okay, here we have a ball that we're lowering. We're holding the string. The speed is decreasing. Okay, so the speed is decreasing. What direction is the velocity? The velocity. It's being lowered. So I just wrote the speed is decreasing. The velocity is going low. It's being lowered. So velocity is down, which is negative. What direction is acceleration? Well, the speed slowing down, the V and A have to have opposite signs. So the acceleration has to be positive. So what direction is acceleration of ball? Positive is upward if we're talking horizontal. So First question is upward. Answer is upward. So don't forget those rules. If B and A have opposite signs, the speed is decreasing. If B and A have the same signs, the speed is increasing. So we're drawing a free body diagram here. So I put the ball at the origin of XY axis. Okay, I'm drawing the I'm showing the tension in the string, upward force is being greater than the weight because the acceleration is the direction of the net force. And we already established that acceleration is positive. So bigger arrow has to be bigger. I mean, the bigger arrow has to be the direction of the net force or the direction of the acceleration. Okay, this guy's in equilibrium, so the horizontal forces have to equal. So I guess the forward force has to be 20 newtons. Let's do the vertical forces now. They're not balanced. They have to equal each other. So I need another 4 newtons going up, right? So you could just, if you want to find the resultant force wells, you could do Pythagorean theorem. Do that. So right here we got 4 free body diagrams determining net force acting on the object. Okay, so so it looks like the vertical forces were balanced, but the horizontal forces are also balanced. So there is no unbalanced force, so net force is 0 in situation A. Let's look at situation B. The vertical forces look like they're balanced, no net force in the vertical, but the horizontal are unbalanced. So the force, the net force would equal 5 newtons to the left. It would equal the friction. Okay, let's situation C. The vertical forces are balanced, but there are no horizontal forces, so there is no net force because the only forces there are balanced. So the situation D, we have in situation D the same thing with no horizontal forces. Excuse me, but vertical forces are not balanced. So net force would be 40 minus 25, which is 15 newtons. 15 newtons up. Okay, so I should put a direction if I'm finding the net force. So I'm going up there and fixing those things. Which is above cases in equilibrium? Well, where F net is 0, that'd be A and C. If you have a net force, you must be accelerating, so that'd be cases B and D. Okay, let's calculate the acceleration in the cases that there is a net force. So use Newton's second law of motion. You need to know it by that name. F net equals ma. So let's plug in for the mass. How did I find the mass? They didn't give it to us, but they gave us the weight. F gravity, gravitational force is the weight. So use that equation to figure out the mass is. The weight is 3 newtons. So 3 newtons equals mass times 10. So it has to be 0.3. I use the equation W equals mg. And it's the same thing here. Move the decimal place to the left, 1 place, divide by 10, 2.5. For the mass. So what I'm writing is m equals weight divided by g, and then just calculating now what the net force is. So we already established that the net force was 5 newtons to the left. The mass is 0.3 using Newton's second law. A is 5 divided by 0.3. That comes out to be tick, 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 tick. 16.7 meters per second squared. Okay, do the same thing for the next problem. Okay, so F net equals MA again. F net is 15 going up. The mass would be 2.5, so 15 equals 2.5 times A. Because I'm still putzing around. Up there, you need to put the direction because acceleration is a vector if I ask you to. Okay, so let's go situation D. F net is 15, subtracted the two forces equals 2.5. Move the decimal point to the left one place. Divide through and you get 6 meters per second squared. What direction? In the direction of bigger force, up. Okay. Next, same thing, except right now, determine the unknown forces. Okay, so they give you F net, and they're missing some forces maybe. So if net force is 0, all the forces are balanced. So A has to be 50 and B has to be 200 to balance out the other vertical or horizontal force. Next one. Oh, F net is 900 newtons up. So C has to be bigger than the weight. Upward arrow has to be bigger than the weight because the net force is up. Okay, so that arrow I'm drawing is C. It has to be bigger. So if I were to write this, 900 F net equals C minus 200. And therefore, just plug in F net. F net divided by, oh, sorry. Can't move that thing, can I? Okay, so you can see C would equal 900 plus 200, which would be 1100 newtons. Okay, going on to the next one, I'm assuming that those two forces are balanced because F net is in the X direction. F net is to the left. So you go 80 minus D is equal to net force 60. So I'm just showing you right there that the vertical forces are obviously equal because F net in the Y direction, F net is not up or down, so it's 0. So let's do the horizontal ones. So F net equals the bigger force of the two, which is the 80 newtons minus D. How do I know 80 newtons is the bigger one? Because they told us that the F net is to the left. So solving for that, D is equal to what? 60 minus 80, 20. 20 newtons. Okay, so going to the next one. The net force is to the right, so I'm assuming these two guys are balanced out, but I have no idea what they are. I just know that they equal each other. But I cannot determine what their sizes are. It could be 3 billion newtons each one. It could be 0.01 newtons. I have no idea. Okay, so there is a net force to the right. So G has to be bigger than 20 newtons. The horizontal force G has to be bigger than 20 newtons. The net force is equal to G minus 20. The bigger one minus the smaller one if they're going opposite directions. So I plug in the numbers and I can see that I just have to add up. Okay, those are kind of, you need to, we did some of those in pos physics. This one's okay. An elevator lifted by a cable is moving upward and slowing down. Okay, so the velocity is, okay, so I'm just drawing the two forces on it, tension and weight. Okay, so there's only two forces and there's one cable. So it can't be that letter D1. It is slowing down. It can't be F net equals 0, choice E. I should have crossed that one out too. Now, if it's moving upward, the velocity is positive. The speed is decreasing because it says it's slowing down. So the signs of A and V have to be opposite. So the acceleration is what? Since the speed is decreasing, B and A have to fight each other. So A has to be negative, therefore down. So net force has to be the same direction as the acceleration. So the net force has to be down. So the arrow pointing down has to be bigger than the arrow pointing up. So it has to be choice C, the third one from the left. Because the one that's pointing down is bigger than the one that's pointing up. Okay, we did these already. Okay. And that's always in the same direction as acceleration. So it's free body of a box on a scale. Okay, so here's, instead of the elevator, here's a box in the elevator. I can hardly see it. Upward force is normal force. And the normal force is the scale reading. Okay, you need to know that. And then the weight is the downward arrow that I can barely see in this stupid video. Okay. Is the elevator accelerating? Yeah, it's unbalanced forces. In what direction? In the direction of the bigger force. Calculating net force. F net equals MA. Well, that's not going to cut it. I don't have A, so I use my free body diagram. So the bigger one says 150 newtons minus the smaller one. It says 100. I can barely read it. Equals 50 newtons. Calculating the mass of the box. Well, W equals mg. The weight was given as 200 newtons. Just move the decimal. Whoop. The weight was given as 100 newtons, so just move the decimal place. One to the left. Calculate the acceleration box if there is one. Yes, there is, because they're unbalanced forces. So use F net equals MA. You have your F net from what we did up there. We have the mass from what we just previously did. Plug it in. Second law, F net equals MA. I get 5 meters per second squared. What direction? Up. Okay, is the elevator moving upward? Is it slowing down? Well, let's figure it out. Velocity is positive. As if it's speeding up, the acceleration is positive because if the speed is speeding up, the V and the A have to have the same size. So if the velocity was positive, the speed would be increasing because we already established fact that acceleration is positive because net force is upward. Okay, so the velocity is downward. A is still positive because of the net force that we figured out before. But if V and A are opposite signs, the speed would be decreasing. So this free body diagram, if they don't tell you what the speed velocity is at the beginning, you don't really know. You can say, well, if it's positive, then whether the speed is increasing or decreasing, and vice versa if it's negative. Okay, here we have simple case. I guess there's no friction yet. Normal force equals the weight if, and it's always perpendicularly up out of the surface. Okay, so we just drew that, and we know that equals the weight because there's no diagonal force acting on it, or it's not in an elevator like we just talked about, accelerating up or down. Okay, what is the size? The normal force equals the weight. I wrote it in the picture 15 minutes. Is it a vertical net force? No, they're balanced. No. If the forces are balanced, there's no net force. Calculate the mass, another name for mass inertia. Well, if you're given the weight, 15 newtons is the weight, you can find the mass again by dividing by 10 using that equation, weight times g. Calculate the acceleration of crate, there's no friction. Okay, g is not the acceleration, okay? That's just used to figure out the weight, the mass from the weight. Now, if it was free falling, g would be the acceleration. Okay, so let's calculate acceleration. There's no friction. Well, there's one unbalanced force. That's called the net force. It's 12 newtons to the right. The mass we just found was 1.5 times A using Newton's second law of motion. A equals 12 divided by 1.5, which equals 2, 3, 4, 5, 6, 8 meters per second squared. To the right. Is the crate shown above in equilibrium? No, because it's accelerating. If you're in equilibrium, your acceleration is 0. So calculate the net force in the crate below if the acceleration is 1 point. Okay, so this might be confusing. We just showed that it was 8 meters per second squared to the right. We'll say the same picture. Okay, that means it's less acceleration, right? That must mean there's friction opposing or drag or something. So calculating net force. Well, if they give me the acceleration, I have the mass. I can find the net force with F net equals ma, but I can't do it from the free body diagram because I don't know what friction is. So F net equals ma, 1.5 times the mass, which was 1.5. So to find that, I'll just wait for it to figure it out. 1.5 times 1.5. And that's newtons. Tick, 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 tick. Oops. So I get 2.25 newtons. That would be to the right. Okay, so the next one I already did. So it has to oppose the 12 newtons to make a lesser acceleration than we saw before. Okay, so let's keep on going. Come on, video. Calculate the friction on the crate. If the acceleration crate is 1.5 meters per second to the left. Okay, so that means the friction, the arrow to the left has to be bigger than the arrow to the right. So that's what I'm writing, the friction of 12 newtons. What? Okay, I think I made an error here. I'm gonna clean it up. I realized it, I guess. So F net is 2.25, that's MA, but it equals friction minus the force. So I hope I go back and fix that. So if it's accelerating to the left, the friction has to be bigger than the force pushing it to the right. So I did that wrong up there. So as I'm remembering, the net force would equal the friction minus the force. So we got to fix that. Okay, I think I'm fixing it right here anyway. Okay, so the acceleration is negative. It's moving to the left. So I put in that little wind arrows wrong. It's moving to the left. Okay, I'm waiting. So the friction has to be to the right. So I want to erase that going to the left arrow. That going to the left arrow isn't really even there. That's the velocity. I shouldn't draw it in like that. Okay. So what I'm doing here, but I'll soon clean it up. Oh yeah, I have to have a force to the right. So that's pretty tricky. I have to have a force to the left because it's moving to the left and friction is opposing it. So the acceleration is negative. I have to have a total force that's bigger, that's going to the left. So did I calculate that? I did not. So I don't know why I didn't calculate it up there in letter L, but it would be F2 is equal to F plus little f. Okay, anyway, I'm just solving for the weight there. It's acceleration of gravity. If it weighed 2 newtons, that's the weight. I'm using the same mass. The mass never changes wherever you are. If you haven't lost or gained atoms, your mass does not change, but your gravitational pull would change. So right there on this place, this planet, the acceleration due to gravity would be 1.3 meters per second squared. If this crate had a string pulling up on it, shown below, calculate force if the floor pushed it up against the floor box width. Okay, well, that's kind of easy. All the forces that point up have to equal the forces that point down. I'm assuming the box isn't lifting up off the ground or digging into the ground. So T plus N equals 15. T plus N equals 15, the weight. So N simply equals 17. Okay, does that upward force affect the acceleration of the block? No, because all the forces are balanced in the vertical direction, but not so in the horizontal direction. Okay, let's move on. Okay, is the coefficient of kinetic friction? Okay, that's that funky mu symbol that some of you think means mass. So that is that symbol right there. That symbol is 0.3. Determine the acceleration of the crate. Okay, same case. So we have friction going towards the left. Don't put 0.3 as the friction. You got to figure out what the friction is. So, since I'm drawing it again, just the horizontal forces, I think. So we got 12 newtons going to the right. Got friction going to the left. So let's solve up for that friction using the coefficient friction equation. So I'm plugging in my numbers to this equation. Move the page a little bit. I'm waiting for my video there. So 0.3 is the coefficient of friction. The normal force, look up at letter N. Normal force is given as 3. So I can't see my work, but you'll see in a minute, in a second. So look, 0.3 equals friction over 3 newtons from previous work in letter M. Comes out to be 9 newtons. You have to plug in. So hold on. Okay, I got to plug in because I'm running out of energy. That's okay. You don't mind me talking. Okay, so here we are. The next question has a diagonal force acting on the box. So, okay, so to finish this one, F net equals MA. We got the F net because we subtracted the 2 horizontal forces. I don't know why I'm going up here. I'm looking for the mass. It's 1.5. So it equals 1.5 times A. A equals, work it out. Divide it through 11.1 divided by 1.5. We get 7.4 meters per second squared. What direction? Look at a picture. Green to the right. If I ask you the direction, you should know. Okay, so let's look at letter Q. Now these diagonal force problems, you gotta break the force into X and Y components. That's the first thing you have to do. Use the equations on your equation sheet. I do the 3-finger rule. Let's see. So do it this way. So, no, this way. Oh, it's backwards. Okay, so you got the X1 and you got the Y1. Look where my fingertips are pointing. Okay, so horizontal one is X, vertical one is Y. You're going to use the equation sheet to find that Fy is F sine of theta. Theta is the angle given. So that'd be 25 times sine of 60. Then Fx is, use the equation sheet, F cosine of theta. So that'd be 25 cosine of 60, which is 12.5. So I'm going to take out my calculator, figure it out. Be sure that you guys are on degrees, not radians. So, tick, 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 tick. So that's the first step of doing these diagonal force problems. You gotta break it down to X and Y pieces, components, and then don't even look at the slanted force anymore or the angle. Who cares about it? It's irrelevant at that point. So back to this problem. Okay, so now I found those. What are we trying to solve for? Okay, so it's like one of the positive physics problems in the last unit where you had to find all this stuff. So just like it, except in that one, they were pulling up on it instead of pushing down at an angle on it. So calculate the coefficient of friction. Okay, I know it has to be to the right. So what is the force that is moving to the left? To oppose that, looks like the Fx, right? So let's find what the friction is. Coefficient of friction is what we're looking for. So I don't really care if it's static or kinetic at this point. But let's plug in our numbers. I can't. All I know is that Fx is opposing it. Well, if it's not moving yet, it's just about to budge from rest. And I'm talking about the maximum static friction. So that equals Fx at that point. So I know that those forces are balanced because it's on the verge of slipping. It's just about to budge from rest. So I do have Fx. I have to find what N is, the normal force. And so we have to look at that. So we got normal force pointing up. We got the weight pointing down. And we got that all the arrows that point downwards have to equal the arrows that point upwards. So be careful, look at it carefully. So we get normal force is equal, don't know why I'm going back up here. I'm finding the weight, I guess, 15 newtons. Okay, come on. Okay, that's the weight, same crate. So 15 newtons is pointing down. So only, okay, is that the only downward force? No. Fy is also a downward force. So I have to add those two and equate it to the normal force because it's in equilibrium vertically. So W plus Fy is equal to N. So I'm going to plug those numbers in. I'm trying to find the N so I can find the coefficient of friction. So 15 plus, already found Fy, 21.7 equals normal force. So that looks like 46.7. Oh, I mean 36.7. Okay. So I calculate that out, and that's my coefficient of friction. So it looks like about 0.3. Yeah, 0.3 about. No units on coefficients. Okay, so we're going to do some more elevator type problems. The crate is off ground, is being pulled upward by force, experiencing acceleration 5 meters. Oh, but has a downward acceleration. So the arrow pointing down has to be bigger than the arrow pointing up because the acceleration is downward. So the net force has to be the same direction as acceleration. So what's the tension in the rope? Well, I have to find that weight. I don't know, I'm looking around, it's 15 newtons. The weight is 15 newtons. So net force is the bigger one, the weight minus the T. Okay, I know the weight is 15 newtons because it's the same crate. Looking for the tension in the rope. Net force is M times A because of Newton's second law. That should have been done first, so you can do it together with this one. The mass we already figured out was 1.5 times 5 is 15 minus T. So T is equal to, get T on the other side, then subtract both sides by 1.5 times 5. So we get 7.5 newtons for the tension going upwards. Next problem is very similar to what we did with, but this is like the positive physics unit 8 problem. Here we were pushing down at an angle. Here we're pulling up at an angle. See the T, the difference of the T's? So we have the same, okay, so let's find, let's find the weight is 15 newtons as it was before. We have to find Tx and Ty, but we already did it. No, we didn't. So there's no normal force because it's suspended in the air. There's no force pushing up against it, so I can say Ty equals the weight. The vertical forces are balanced. So you know what Ty is. And let's find what Tx is. Well, if I have an angle and a leg of the triangle, I can find the hypotenuse using one of those equations on the equation sheet. So Ty is 15. And so Ty is T times sine of 40. That's on the equation sheet. So I don't know where I'm waiting. Oh, I realized something. Okay. I'm thinking of something. Okay, so we find out that that is equal to 15 is Ty. T, I don't know. That's what I'm trying to find. Sine of 40. So I'm going to calculate out. And I have to do 15 divided by sine of 40. Because I'm solving for T. So that comes out to be 23.3 newtons. Now I made a mistake in my picture because if this is an equilibrium, the leftward arrow should be the same as Tx. So I'm gonna, if I were to ask you to find Tx, I'm sorry, if I were to ask you to find the tension in that horizontal rope, that purple line right there, you should understand that it's not 100, it can't be 100. It has to be the same as Tx. So what is Tx? I didn't find it yet. Tx is T times sine, cosine of 40. T times cosine of 40. Well, low. I'm just showing you that these don't equal because I made a mistake with the 100 there. So I just did 23 cosine of 40, and it shows you that sure isn't 100, it's 17.61. So what I have to do is just change that up there, erase the 100 newtons. That shouldn't have been there, I just guessed at that. And put in 23 times cosine of 40, which is what is it? A big blue blob. 817. Okay, so Tx is 17, and it's the same as the horizontal force pointing to the left. So that 100 newton was a mistake that I just threw in. So see that blue triangle? Tx does not equal 100. It equals 23 cosine of 40, which is 17 newtons. It's not 100 newtons. Having issues here. I'm just going through it again. So tension in a string is equal to Tx. I found Tx in blue down there. And so just waiting to write it over again. So Tx equals T1, tension in the rope, right there, which was 17 newtons. I don't know why I erased it. What? Experience a greater contact force, a baseball hit. Okay, you need to know the third law of motion. It doesn't matter who hits who. They both experience the same force. If one's bigger, one's hitting harder than the other, like a bat. I mean, just so you know, if object A pushes object B pushes back with the same speed, no matter who's going faster at the first or who's bigger at the beginning. And the third law makes it very simple. Forces have to equal contact forces. Next one. Okay, so these kind of questions, you just look at F net equals MA. A had triple the mass, so if it has triple the mass and the same net force, how can you make the net forces stay the same? If you triple the mass, you have to 1/3 the acceleration to keep the net force the same. So basically what I'm saying is M and A are inversely proportional. By whatever factor you change the mass, you have to change the acceleration. The acceleration becomes 1/over that factor because M and A are inversely proportional. You need to know that. That's the next question. So in this problem, if I said, well, if I halved the mass, what would happen to the acceleration if you want to apply the same net force? Well, 1/2 times what is 1? Acceleration will be 2 times as great. So what am I doing there? Oh, I'm just plugging in numbers to show you that the acceleration will be 1/3 as much. You don't have to do that. Okay, next one. Newton's second law for a given mass, net forces are inversely proportional. Okay, these problems, I just picked some that would be good. reviews. There's a bunch of these that you can do, but we've done them similar to them anyway. So I'm going to draw an object moving at constant velocity. Okay, so moving at constant velocity, the forces have to be balanced, so the opposing force to whatever force is pushing it has to equal 20 newtons to the left. So it's 20 newtons. So the forces have to be balanced. You have to be in equilibrium if you're going constant speed, velocity, constant velocity, or if you're at rest. Okay, next one. So this lady's standing on a spring scale inside an elevator. If the scale reads the normal force applied, okay, I shouldn't tell you that. The scale reads the normal force. I'm erasing this so you get some more space to see my writing. What would it read when the elevator is coming downward at 3 meters per second squared? So let's draw a picture, 3-by diagram. It's going down, accelerating downward. The weight has to be bigger than the scale reading, which is the normal force. Oh, her weight's 10 times her mass, right? mg. How do you know 50 kilograms is her mass? Because it says kilograms. So I'm going to make the normal force a smaller arrow than the weight because the net force has to be downward. So I know F net equals MA, and I know F net equals the bigger minus the smaller, W minus N. So I could equate those two. So what am I going to show you here? F net equals 500 minus N, the weight minus N, but it also equals MA. So I can solve for MA. 50 times 10 is 500. Oh, I'm sorry. A is not 10. A is 3 meters per second. So 50 times 3 equals mg, 500 minus n. So n would have to equal 500 minus 150, which equals 350 newtons. So that's what the scale reads. Okay, it reads less than what she really weighs. 350 compared to 500 newtons. Okay, so next. Okay. Okay, so the forces look like they're balanced, the normal force and the weight. So it could be at rest, but it doesn't have to be at rest. It could be moving at constant velocity upward or downward. Usually I draw it so that those two origins are at the same place. I don't know why this picture is not showing it. So origin is usually at the center of mass. So it would look like this. Forces are balanced, but it's in equilibrium. But equilibrium means either moving at constant speed or constant velocity, I mean, or at rest. Don't just say at rest. What is the normal force surrounded by? Well, since this balance, normal force is 0. I'm sorry, the net force is 0. Don't get that confused. This both starts with a capital. This both start with N, net force and normal force. Normal force is balanced by the weight. Normal force equals the weight. Is equal to the mass times equals the weight. Mass times G. Moving at constant velocity, yes, towards the left. Well, I don't know if it's moving towards the left. Okay, but yeah, it's moving to the right because friction, little f, is opposing the velocity always. So no, it's moving towards the right in the presence of friction at constant velocity if friction and force applied are the same. Okay, so that was false. Not, it is move. It could be moving at constant speed. It could be at rest if that's static friction. So two things make this. I mean, it's not necessarily moving, but it's totally not moving at all to the left because friction is to the left. It has to be moving to the right. Parakeets. Okay, let's go to the next one. What's the big lag about? Okay, the next one, move it. Move it to the screen. What am I doing? I'm talking. Okay, let's go with this one. Number 18. Which choice is correct? This actually would be losing speed, gaining speed, or okay, if I take my fingers and compare the lengths, they're both the same. So it could be moving at a constant velocity, it could be at rest. So it's either one of those is correct. But I'm not sure which one it would be from just the picture. Okay, I guess I'm using so number 22, I guess I'm looking at now. Which choice this object is, okay, not vertically, it's balanced vertically, but looks like it's moving to the right. Is it gaining speed? Why? Because the force applied to the right is bigger than the force of friction. I know it's moving to the right because friction is pointing to the left, opposite. So I guess I skipped it 18. Oh, wait, 18. Okay. Okay, let's look at number 24. This free body would only apply to an object being raised vertically or at constant velocity. No. Again, tension has to equal weight. It could be at rest. It could be moving downwards at constant speed. It could be moving upwards at constant velocity. So it's false. Number 25. The answer to that is what is the magnitude of tension and strain? Wow. It would have to equal. It would have to equal the weight. Okay, so it'd be mg 3 times 10 or 30 newtons. Okay. Next one. Which choice is correct? Okay, mg is bigger than the tension, so the acceleration is down. So we already did this problem. If the velocity is down, negative, acceleration is down because weight's bigger than the tension. So both the acceleration and velocity have the same direction, so the speed will be increasing if it's going down. So it could be falling, going down and increasing speed, or it could be rising if velocity is positive and acceleration is negative, like I'm drawing here. The speed would be decreasing. So it could be going up, but slowing down. Or it could just easily be, because velocity isn't mentioned, it could be the other case, the speed increasing. It could be rising with decreasing speed. So it could be the first choice or I could just explain. Wish the screen wasn't down that far. So it could be falling and gaining speed, like I just explained down on the right side. A is negative, B is negative, so it'd be gaining speed. Or it could be rising, and you can see that A and B are opposite directions on the left, and losing speed. So it could be either one of those choices. Okay, I wouldn't give you this on a test unless I said pick two correct choices. Okay, look at this one. Okay, so we did these already. So this is just a review of what we did already. We got a diagonal force pulling upwards. You got to break that diagonal force into x and y pieces, ty and tx. There's an equation for an equation sheet for these. So that's what I'm going to do right now. Tx equals, oh, and it's in equilibrium at constant velocity. That means that horizontal forces equal each other. Ty plus n, the total force is going upward has to equal the force going downward. So what's the size of the magnet of the frictional force? It's going constant speed. It has to equal the tx on the other side. Look at your diagram. Friction has to equal tx. So tx 15 cosine of 37 t cosine of theta on your equation sheet. So we can calculate on our calculator. Then find the tension, the normal force. Look at the picture. Ty plus normal force N is equal to the weight pointing down. Because both those in this case are pointing up, Ty and N. So putting in, don't forget the weight is 10 times mass. It's equal to Ty, which is 15 sine of 37, 15 T sine theta. So we can find N that way. So we got to calculate that out. Okay, so I guess I was too lazy to calculate it out. Okay, so number 34. Again, we're pushing down with a diagonal force, so we got to find x and y components first. This is going at constant velocity, which piece equals the friction, right? The horizontal piece. Because it's going frictional speed, constant speed, the friction has to equal the forward part of the push. So I'm finding fx. It's f cosine of 70, which is 15 cosine 37 on your equation sheet. So whatever that is, you can use your calculator. And what is the numerical value of the normal force? Okay, normal force points up. Fy points down, weight points down. So Wy plus Fy equals normal force. So let's find Fy. That would be F sine of theta, 15 sine of 37. Plus weight is mg, 50 equals the normal force. So because I have a need to find numerical value, I'm going to do that. Oops. Looks like I'm making a mistake there. Sine 37 equals plus 50. So I didn't realize I had made a mistake, so I'm gonna go back to it. Oh, I gotta fix that. It's not 14.97. Go back to my calculator. I think I realized that. Fall asleep. Okay, so I'm gonna fix that one up. So 15 sine of 37 is equal to I guess I didn't fix it on my work, but I did fix it on the final calculation. So 15 sine of 37 is about 8, not 14.97. Okay, so the coefficient of friction is the friction over the normal force. Friction is whatever 15 cosine of 37 is. So friction is equal to Fx like we said before. So it's 12 over 58. 12 over 58 is equal to whatever. So that's kind of review. And in this case, the size of the normal force is what? Greater than the actual weight because it's being pushed down on. If you're on a scale and someone's pushing down on you, diagonally down on you, the scale readings n is going to be greater than the object's weight, so that's false. Okay. That circle false. Okay, I think we're getting done with this. Oh, no. Come on. Sorry. Okay, let's easy skip. Go to the next page, Mr. Noise. Go to the next page. Okay, right here. Okay, again, if you read that, doesn't matter what their masses are, how fast one's going compared to the other. If one knocks into another one or pulls on another one, no matter what the result is, the forces applied by one is equal but opposite in direction to the forces applied by the other one. So it has to be letter D. Okay, that's a good one. Curling rock is traveling to the right. Cross ice is shown. Which if found best to describe force acting on the curling rock. Okay, well, you have no force and weight, of course, because it's on a surface. So you have to have up and down forces, and they have to equal each other. There's a weight, there's a normal force. And just because it's going forward doesn't mean there's a forward force. But because even though it's on ice, there still is friction opposing the motions. I'm going to draw as the arrow pointing to the left. There's no forward pushing force at all. So it has to be that picture right there. Okay. Let's look at number 59, I think. Which one did I do first? So number 50, I guess I did 56 first. So I have mass, I have acceleration, I can find the net force, MA. But I have tension in the cord, that's like the drag pulling the car back. So I guess he's not pushing on the gas. The only unbalanced force is the tension holding him back. So it'd be the net force, would be the tension. And that comes out to be 10 times. So many newtons. Oh. So 2025 is like 2,000, which is 2 times 10 to 3. Okay, let's go 59. Black in the diagram being accelerated to the right. Okay, so the tension has to be greater than the frictional force. It's not a rough surface, so it's friction. So, but I also have normal force and weight balancing out. So which one has the forward force, tension being bigger than the friction? What do you want? Oh, you can talk to her. Okay, so there you see what the free body diagram would be. That matches letter D. Okay, let's look at number 60. Eventually. Okay, a 5 kilogram block is being pulled to the right by a 75 Newton force. What is the normal force on this block? Oh. Okay, we've done this before. We have to find Ty. Ty is 75 times sine of 20. It's, no, that's not the normal force. That's just it's one of the upward forces. Normal force for pushing up against the block. Normal force plus the Ty equals the weight. The mass is 5 kilograms. So weight is 50 newtons. So N plus Ty has to equal 50. So should be able to do that. Those are the trickiest ones there are. Okay, so Ty is T 75 times sine of 20. So I can find that, substitute it in for Ty. And so, which I'll slowly do here, I guess. And I believe that's it. So I'm going to calculate t sine of theta, 75 sine of 20. You get 25.6, 26. Subtracting those, I get the normal force, which I cut off the choices. So what's that come out to be? That comes out to be 24.3 newtons. 24.3. Okay, so I think that's the rest. That's it. So I'm just comparing it to this one where I push down. Very similar, but I'm pulling up with a diagonal force in the problem I just did. So I think that's it. I believe that's it. Okay, so I might just look at this right here. Okay, so I'm gonna stop this, and I'm gonna end